Hello, everyone. Good evening to all of you, and welcome to Unacademy. Welcome to the series of NCERT, where we are actually discussing the NCERT books and the fundamentals of physical geography. Now that we are almost able to finish the portion, now we have only one other class left. I hope that we have developed the conceptual clarity which the subject of geography does require for the examination of civil services. Today, we are going to initiate the discussion for the unit of oceanography. Now, oceanography is an entirety of the unit, which is very rewarding from the point of view of the examination because here, not many complexities are involved. And any candidate who has understood the portion such as geomorphology, etc., for them, oceanography is a direct flow. And for them, it is very easy to understand. UPSC also asks you very direct questions. No complexity, no further complications. So, this is one of the low hanging fruits and one of the most scoring areas when it will come to the prelims as well as the mains examination. The questions are repeated. The same questions are repeated in the mains exam as well. Now, in the case of climate, here the global climate or the world climate, that is again one of the areas from where UPSC will ask you question in the prelims examination. This year it was not asked, but almost every other year you have a question asked from the Köppen classification or the world climate. Please do take a look at this particular chapter and ensure that you have understood this chapter so that if possible tomorrow we can also have a discussion of the PYQs associated with the chapter of climate classification as well. Prior to that, I will hold you accountable for some of the discussions that we have had. I will check whether we have understood the concepts in clarity or not with the help of a couple of PYQs asked last year, that is in 2025. Take a look at this question. So, here, consider the following statements. Amount of dust particles in the atmosphere is more in subtropical and temperate areas than in equatorial and polar regions. Statement 2. Subtropical and temperate areas have less of the dry winds. Let me know what is the answer of this particular question. Whenever statement based questions are asked, first thing that you have to check is whether both the statements are correct or not. Once you are sure that both the statements are correct, then you will take a look at it if they are associated or pertaining to the same topic. Answer will be option A. If they are pertaining to different topics, option B will be the answer. However, the work is much easier if either of the statements are incorrect. That is the case in this previous year question as well. In this question, statement 2, statement 1, the amount of dust particles in the atmosphere is more in subtropical and temperate areas than in equatorial and polar regions. Is the statement correct? The answer is yes. Why? Because in the equatorial regions, you have the case of rising air. This rising air will lead to formation of convective clouds. And these convective clouds will eventually bring rainfall. Wherever you have rainfall, there will be lesser amount of dust particles. Whereas in subtropical region, you have dry conditions, lack of rainfall, desertified areas. That is why there will be more dust particles. So statement 1 is correct. Statement 2, subtropical and temperate areas have less dry winds. This is incorrect. Here, you have more dry winds in subtropical regions because of an absolute lack of rainfall. So, the correct answer in this case is C. Take a look at this particular question associated with isotherms just to see whether we retain the learning from the isotherms or whether we have forgotten it like the summer sky. So, consider the following statements. In January, in the northern hemisphere, the isotherms bend equatorwards while crossing the land masses and polewards while crossing the oceans. In January, the air over the oceans is warmer than that over the land masses in the northern hemisphere. So, here, what is the correct answer in this? So, first test whether both the statements are correct or not. The answer is yes. Both the statements are absolutely correct, right? So, nor the isotherms bend equatorwards while crossing land masses and polewards while crossing the oceans. We have seen that in the winter months, the isotherms bend polewards while moving to oceans. Why? Because the oceans are warmer than land at the same latitude, because the land gets much more colder. So here the first statement is correct. Second statement, air over the oceans is warmer. This is also correct. So the correct answer in this case is going to be A. Okay. Now, we will be discussing the questions associated with the world climate tomorrow. I expect you that after this session or before tomorrow's session, you should have watched this particular session as well. After that, we shall have a fruitful discussion of the PYQs associated with that chapter tomorrow as well. Okay. Now, coming to this chapter number 12. And this, in fact, in itself is a story of how we have basically devoted more time into the concepts. We are almost into the 16th or the 17th class covering chapter 12. So we have paid sufficient attention. All that is required out of you is revision. You revise it, and from within the next few days, I will give you a link, or I will tell you how to download the notes as well. I will give you the concise notes also of all these particular sessions so that it becomes easier to revise. But before that, I need you to complete the revision portion. Now, this is the case of oceans. Now, when you study oceanography, oceanography is what? Study of the oceans. As simple as that. Okay? How you study the oceans. Now, study of oceans in the world, let me give you a brief background as well. That study of oceans in the world is something which was initially very limited. The depth is basically the case of the depth of the ocean was restricted, right? And idea of the depth is what people got to know. Beyond that, people did not have much of an understanding of the temperature, the variation, the ocean currents, etc. However, it was during the era of the the colonialism in itself, when you had the Spanish and the Portuguese colonialists and the sailors and the merchants who would travel the oceans of the world. They for the first time gave an idea to the people that, look, when you go out in the ocean, there is a natural movement that the ocean does have. That natural movement carries you automatically from point A to point B. That is when you had various different sailors like Leon de Pons, who basically gave the idea that there is an ocean current named as the Gulf Stream. There is something known as the Sargasso Sea. So all of this was given in the 1400s, the 1500s, and the 1600s. But still, what lies underneath the ocean, that is something which we got a detailed idea about in the 1900s. And when did we get an idea about that? Only after you had the exploration done post the Second World War. We have talked about it that during the Second World War, in order to detect the German submarines, the Allies and the Allied forces, they started developing the sonar system, and they attached it with every vessel and every ship. Post the Second World War, those sonar systems were then used to map out the ocean floor. Earlier, the belief was that just like how the ocean surface appears to be flat, similarly, the ocean floor would also have been very, very flat. Later on, people woke up to the reality that underneath the oceans also you have volcanic mountains, you have plateau-like features, you have these ridges which are continuous for more than 70,000 kilometers. Now, all this idea improved our understanding of how the oceans behave. Now, for ease of study, I would ask you to divide this oceanography into two groups. One is the case of the ocean bottom relief. In fact, three groups rather. Now, this has got direct linkage to the case of geomorphology. Okay. It has got the direct linkage to geomorphology. How what we have studied about volcanism, how we have studied about seafloor spreading, that explains the case of the ocean bottom relief. Then other group is physical properties of oceanic water. Physical properties. Now, what do we mean by physical properties? Variation in temperature, variation in salinity, the amount of salt content. So that is the case of temperature and salinity. Then you have movement in oceans. In oceans. And under this, we will come across the case of why waves occur. Why do you have the occurrence of tides and also ocean currents? Okay. So these are the areas that how you can divide oceanography and how you should actually approach and study this subject. Okay. Now, this chapter deals with these two portions. That is what we are going to cover today. Okay. Now, when we say the oceans of the world, oceans dominate the surface of planet Earth. The Pacific is one of the largest oceans, is the largest ocean of the world. And in fact, you have the saying that we know better about the Martian surface as compared to our ocean bottoms. Because the depth of these oceans oftentimes spanning for 5 kilometers, 6 kilometers deeper from the surface, you do not have adequate machinery to go at the bottom and actually look at the surface. We still do not have a lot of idea about the type of fishes, the type of species which live in the ocean floor. It was only a few years ago that we came across the species of black coral. And later on, we got to know the lifespan of black coral. One black coral can have a lifespan stretching for more than 3,000 to 4,000 years. So we did not have much idea, and we still do not have much idea about what lies at the ocean bottom. That is why study of ocean becomes very important. Also, the fact that when we talk about these oceans, through their movement of the ocean current, through the absorption of the air above, they play a very important role in the heat balance and the heat budget of planet Earth. These oceans, they absorb the atmospheric carbon dioxide, and that is where they can also reduce the amount of greenhouse gases which are present in the atmosphere at any point of time. And one should not forget, life on planet Earth began underneath the oceans. And that is where life existed for a very long period of time before life basically moved across to the land areas. The evolution of life is something that we will be discussing whenever we start the case of the NCERT of environment. We'll be discussing there. But having said that, that is why the study of oceans is a must. But when we talk about the oceans across the world or the water distribution across the world, majority of the water across planet Earth is trapped in the oceans, and that water is saline, salty. Fresh water is very, very restricted. Almost around 97.5% of the water across the planet Earth is saline. Most of that trapped in the oceans of the world. Only around 2.5% of the water across the world is fresh water, and that too majority of it in the ice caps and the ice sheets, and the remaining in groundwater, very minuscule fraction in the form of the rivers and the ponds. So understanding the ocean becomes important, but the most important part here is the ocean bottom. Now I always say that when you were a kid and your teacher would have given you certain number of crayons, that draw the land and the water, you would have taken any kind of blue color and you would have colored the water body, indicating that this is an ocean. Never have we realized while looking at a map that the depth of the ocean is different in different areas. The shade of blue indicates the depth here. For example, if you observe these regions immediately off the coast of India, very light blue, isn't it? Very light blue. These are the regions which are the shallowest, which are at the least depth. Okay. So these are the areas which are almost an extension of land. Then observe this kind of a fracture like shape. These are your mid oceanic ridges, areas of active volcanism or the spread of the oceans. Okay. Observe this. Then you have these regions of the oceanic trenches, the deepest part of the ocean. It is here that you have the Mariana Trench, the deepest part across the ocean floor. Kanti, yes, we will continue with Indian geography as well after a brief moment of time. I don't want to overflood the information. I don't want you to start hating geography at the end of it. I will give you some brief amount of time. In the meanwhile, you will have some other subject NCRTs. Then within a month, we will start with the NCRT of Indian geography as well. Okay. Now, here, these basic differences in the ocean bottom, that is what we refer to as the ocean bottom relief. Relief here basically indicates the physiographic classifications and the physiographic variations which are present on the ocean floor. Now, this map or this kind of image is also very important for you to understand. This tells you about the variabilities and the variation in the ocean floor. Let us study through this map itself. Images always teach you more than what the text can ever make you learn. So, pay attention to this image. This is the portion of land. I don't think anybody will have a doubt in that. Observe here that the slope of the land is continuing here itself. This is the part of the water. The blue part is water. But observe here that the slope of the land is continuing. Right. So the feature that the land indicated in the coastal area is almost a continuous portion. This is a portion which is known as the continental shelf. Okay. It is known as a shelf. Just like you have shelves out there in your room as well. So this is like an extension of the land. Okay. Now, at one point of time, you observe that suddenly the shelf ends and you basically have the gradient or the slope increases. This is what is this point where the continental shelf ends is known as shelf break. Now, kindly pay attention. When we talk about these continental shelves, their depth will be somewhere around 30 meters to maybe at max around 500, 600 meters, right? But for how long do they extend? Okay. For how long do they extend? That varies, right? In certain areas, they can be very short. In certain areas, they can be very long. What determines their extension into the sea? It is basically the feature of the land. For example, if let's suppose I have a hill in the region of the coastline, the shelf area will be very small. If I have a plain region in the area of the coastline, the shelf will be very large. So that is where the shelf and its extension varies. Now, observe this map. If you will observe This map indicates this light blue color, that is the shelf. Very wide here, isn't it? Very wide here, around the region of Siberia, Arctic. But observe the shelf in this region. Observe the shelf in this region. Almost absent. Why? Because here you have volcanic mountains on the coastline. So continental shelf is variable, not everywhere it is present, right? But then these are the areas of shallow depth. Means what? Means sunlight is available. Now, wherever sunlight is available, I will have aquatic and marine plants also which will grow. If marine plants are there, herbivore, carnivore, everyone will come across. So biodiversity will be higher. So this shelf area, if you take a look at this map, you will observe that the shelf area is not very dominant, isn't it? Shelf area, believe it, is roughly around 8 to 10% of the overall global ocean. All the oceans combined, shelf area is only 8 to 10%. That's it. But they account for more than or around 90% of the known oceanic biodiversity. So that tells you how important this shelf area is going to be, because they lie in the zone where sunlight is received. Now, from this, another set of derivations. When we talk about the shelf area, okay, whenever we talk about, let's suppose, the shelf area. Now, here sunlight is available, plants will grow, marine organisms will be there in large numbers. Let's suppose there is any kind of landslide or submarine slide. It can happen that lot of these organisms can die in the same place. Marine organisms can be deposited and fossilized over a period of time. It is this fossils and the remains of marine organisms which over a period of millions of years gets converted into fossil fuel, that is crude oil, petroleum and natural gas. That is where you will observe that these regions very rich in oil, these regions very rich in natural gas and oil, this area, North Sea, very rich in oil. Everywhere you hear about Norway doing so well, Norway being the best in the taxation, in the social services. Why? Was it always the case? No, oil is there. Then, even in India's coast, Bombay High, in the continental shelf area, Gulf of Mexico, continental shelf area, Guinea coast, continental shelf area. That is where shelf areas are very rich in oil reserves. This is the reason why we have started exploring the region of Andaman Nicobar. And we have found oil even in the region of Andaman Nicobar Islands. So that is the case of this continental shelf and its linkage with the fossil fuel. Beyond this, suddenly the gradient increases, the slope increases. This is what is referred to as the portion of the continental slope. It is here that it can be very, very deep. It can have a depth of almost around 3,000 meters also. It can carry you to the depth of 3 kilometers from the surface, right? So suddenly the depth increases. Then after that, you have the portion which is continental rise. This is nothing but a series of deposits which the ocean has dragged from this region and has dumped it into this area. This continental rise is not going to be consistent everywhere across the coastline. In certain areas, it is present, in certain areas, it can be absent also. A combination of continental shelf, a continental slope, and a continental rise together, all of them combined, is referred to as a continental margin. Meaning what? That this is the extension of the landmass. And the feature of the landmass will also be found in these areas. Either deposits, from the landmass. Let's suppose the rivers have carried out certain deposits, it can be deposited in these areas also. Beyond this, what starts is the oceanic plain. Large, endless, dark plains where sunlight never reaches the bottom, right? That is the case of what is also known as the abyssal plain. Tarai, in what sense? In the sense of deposits? Are you talking about the deposits and then comparing it? No, yes, Manisha, you are correct. Like an alluvial fan deposit that you have. Okay, that kind of deposit can be uh, having an analogy with the continental rise. Okay, now here, basically, when we talk about the division of the ocean floor, you have the major relief features and you also have minor relief features. Major relief features which occupy a larger area, which are quite prominent. So, amongst the major relief features, you basically have the case of continental shelf, continental slope. I told you, continental rise is not present everywhere. Certain regions, continental rise can be absent as well. So that is why not considered a major relief feature. Then you have the case of deep sea plains, and then you also have the case of oceanic trenches or the ocean deeps. These are referred to as the major relief features, right? Let's take a look at each of them one by one, and then we will understand the minor ocean relief features as well. So the continental shelf is simply an extension of landmass, isn't it? Now, its extent will vary based upon what is the coastal feature. If coastal mountains are there, if coastline has mountains, in that case, shelf will be very short, will be short. Now, if coastline is a plain, is a plain, in that particular case, shelf is elongated, right? For example, in the region of Siberia that I showed you, in that particular case, the shelf is as wide as almost 1500 kilometers. Okay. Whereas in the Sumatran coastline, in the Philippine coastline, in the South American coastline, it is very, very small. Okay. Soft rock, it cannot be present for the entirety of the stretch. Soft rock will be present to some extent. There it will be eroded, right? After that, you will have hard rock only. So, mostly determined by the case of the land features. Okay. Now, here, if you observe the map of India, you will observe the case of the coastline, right? Now, if you observe the coastline here, basically, the whitish color that you see, the whitish color that appears, this is the case of the continental shelf. You would see that you have the continental shelf both across the eastern and the western coast. Now, this is where the majority of the people get a confusion. Majority of the educators also I've seen teaching wrong in this, because in certain places it is mentioned incorrectly in the books. Now, if you observe the coast of the Western Ghat, Western Ghat is a mountainous feature, and then you have the sea. Whereas Eastern coast is a plain-like feature, and then you have the sea. Still, you have the case of the continental shelf being much wider across the western coast, whereas across the eastern coast, continental shelf is much narrower. Why? The reason here is basically because of the endogenic force. Over the past few millions of years, what has happened in the Western Ghats or the Western coast is that you have had a fault creation. And that portion has actually, earlier, Western coast was somewhat like this. Millions of years ago, India had a Western coast like this. But as the collision with the Himalayas did happen, thereby a lot of stress was created and a fracture which existed here meant that this portion simply sank. Okay. As it sank, meant what? That now the new relief feature was somewhat like this. So, this submerged portion is the new continental shelf and is the reason why the continental shelf is very broad there. The evidence of it, off the coast of Mumbai, you have evidences of submerged forests, right? In fact, this submergence is something which is very continuous from the region of the Gujarat, Kutch, Kathiawar coastline all the way to the region of Kerala coastline. Whereas across the eastern coast, what has happened? Over a period of time, the epirogenic forces, we have studied diastrophism and sudden forces. Epirogenic means vertical movement. Epirogenic forces have led the Eastern Ghats to emerge above the sea surface. That is why the shelf has been narrow in this particular region. So it is these internal tectonic forces which have resulted in the submergence in the Western Ghats, the emergence in the Eastern Ghats. This is the reason why even today oil is to be extracted from this area, Bombay High, and the government has been exploring the oil reserves across the region of the Krishna Godavari basin. It has emerged, it was underwater, and now the latest drilling has been happening across the Mahanadi basin. So that tells you where oil reserves are generally found. Okay. Eastern coast, basically, eastern coast has emerged above water. That is why eastern coast is also referred to as an emergent coast. Okay. So it has basically risen above water. That is why the shelf area is very narrow across the region of the eastern coastline. Whereas across the western coastline, it has sunk. Okay. So western coast, submergence, submergence has happened, right? And eastern coast, emergence has happened. Emergence. Why has it emerged? Remember, we had discussed while we were talking about the interior forces of Earth. We were talking about the case that because of the internal heat, the land can be pushed up, the land can sink as well, right? There is a vertical movement up and down, what is referred to as the apirogenic forces. So, those apirogenic forces, not recently, over a period in the past when India was still moving northwards, to the north of equator, at that point of time, the apirogenic forces push the coastline above. Okay. In the portion of your uh, geography optional, you read something known as isostasy. That is maintaining of mechanical balance across the planet surface. So in simplest of that format, it tells you that one portion it sinks, other portion emerges. It is not the exact cause here, but it is a natural causation over a longer period of time that you will have the lower density portion which is going to be uplifted. So that is where the internal heat pushed the eastern coast upwards and created an emergent coastline, creating lot of oil avenues in the region of the Krishna Godavari basin and the Mahanadi basin as well, right? Colorado Plateau is another example. Colorado Plateau is the case where upliftment has happened in between, not in the coastal area. That kind of upliftment in India has been experienced in the Chota Nagpur Plateau. That is why Chota Nagpur Plateau today you will observe that batholites are exposed to the outside surface, isn't it? The Ranchi batholith, famous one. How did it happen? Over a period of time, there has been an upliftment. So that is why you will find the incised meanders, the case of the waterfalls in the region of Chota Nagpur Plateau. But the only difference between Colorado Plateau and Chota Nagpur Plateau is Chota Nagpur Plateau is volcanic, created out of igneous rocks, whereas when we talk about the case of Colorado Plateau, we have covered it in the mapping sessions, it is of sedimentary rock, right? You have the Colorado River, which has deposited these sedimentary features. Okay. Now, please do not mistake this to understand that only upliftment will lead to the presence of oil reserves. Oil reserves can be found in the continental areas as well. Please get that very clear. Okay. In the western coast, there is no upliftment. Still, you have Bombay High and the region around the Ankleshwar. So wherever you have the submergent coast, there also offshore oil reserves can be found. That is the case in Venezuela, right? There you have the submergent coast. You have escarpment in the coastline of Venezuela. Onshore oil reserves are found wherever there you have the fault lines where a lot of water has accumulated, aquatic animals have died, deposited, oil can be created. Okay. So that is why you have oil across the Jorhat basin. You have the oil across this area, oil across the region of the Shekhawati belt in Rajasthan. Why? Because historically, Rajasthan was also underwater. Okay. This is the reason why western coast is more suitable for port cities, because near the coastline you have deeper waters, land has submerged. Here, the near the coastline you have shallow waters. To have an ideal port, what do you need? That exactly near the coastline you should have deeper waters. That is what is requirement of a natural port, which is present across the western coastline. In most of the cases, Tarak, that is correct. Okay. Now we move beyond the shelf area. Beyond the shelf area, the slope increases. That is a continental slope. Here you will find that at the bottom, by the time that you get to the bottom of the continental slope, sunlight is not able to reach. Here, the gradient can be as much as 60-degree incline. That can be the amount of gradient here. Okay, 60-degree incline. And here you will also find the case that basically top portion you will have the case of certain plants, aquatic plants obviously, but the bottom portion, aquatic plants will not be there. There are a couple of reasons for that. First, light is not there, so lot of aquatic plants won't be there. Secondly, this is a zone where you have lot of these submarine landslides, submarine mass movements occur in large numbers. So wherever you have lot of materials which keep on falling down, you won't have lot of surface on which plants will grow. So oftentimes barren rocks are exposed at the bottom of the continental slope. Depth, it can carry you to the depth of almost 3,000 meters from surface, 3 kilometers, which is huge. Okay, that is the case of the slope. Then you have vast areas of absolute darkness, what is known as the deep sea plain, or also referred to as the abyssal plains. Okay, abyss is an English term meaning something which is absolutely at the bottom, right? The failure led me into an emotional abyss, right? I was at an absolute emotional bottom. So that is abyss, from that abyssal. Okay. So abyssal plain or deep sea plain basically means absolute bottom. It is large areas of very flat condition. Now, what do you have at these deep sea plains? Light has never, in many of the oceans, I'm not talking about regions like, for example, some of the shallow lakes or some of the lakes and the Caspian Sea, etc. I'm talking about oceans of the world, five oceans of the world, right? Here, the depth on an average is 4 to 5 kilometers. It can be more as well. So, what do you have at the ocean bottom? At the ocean bottom, you will find, first of all, deposits of various different types. Which kind of deposits? So, there is, first of all, some of the sedimentary deposit, very less amount, however. Sedimentary deposit is very less. Why very less? Because most of the deposits which had to come from the land areas, etc., they will get dumped either in the shelf or the slope or the case of the rise. They won't be reaching up till the level of the abyssal plain. So that is why sedimentary deposit is very less. Other than that, you will find deposits of dead species, right? Diatoms, radiolurina, globigerina, right? These particular individual species, microscopic, dead microbial deposits. And then after that, in large numbers, huge numbers, you will find deposits of iron, potassium, right? Some silicates, very little amount, however. So these kind of deposits will be found in large number. In many of these cases, I hope you are able to see some of them form these large nodules where multiple different minerals combine and then they sink. These are rich in multiple metallic minerals, manganese and iron being dominant out of them. That is why, and they will also have nickel, cobalt, chromium, these kind of minerals will also be there. That is why these are what are referred to as polymetallic nodules. They will have multiple metallic aspects within them. So those polymetallic nodules will be found in the region of these deep sea plains. Okay. Now, then this is not the deepest part of the ocean. Which is the deepest portion of the ocean? It is the case of ocean deeps or trenches. Oceanic trench is found in zones of convergence and subduction. We have studied this in the case of geomorphology, that whenever you have an oceanic plate which undergoes subduction, in that case, there is a sinking which creates the trench. Okay. So, whenever you have oceanic convergence, and oceanic convergence leading to subduction, there either oceanic or even oceanic continental, any of those. But you need to have an oceanic convergence. Whenever that is created, you will have these trenches, right? So Pacific plate is subducting across the western side. You have the Japan Trench, you have the Kurile Trench, you have the Mariana Trench, and Indian Ocean on the eastern coast. You have the Java Trench, the Sunda Trench. All of these are situated. In fact, you also have the Andaman Trench. Just before the Andaman Nicobar Islands, you have the case of oceanic floor undergoing subduction. So that is where you have these ocean deeps. These are your major relief features across the oceans. And now coming to the case of the minor oceanic features. Which are the minor oceanic features? One of the minor oceanic features is the case of mid-oceanic ridges. Mid-oceanic ridges are the sites of active volcanic activities. Volcanic activities. We have studied in the case of seafloor spreading in the third chapter itself that how these mid-oceanic ridges from here volcanic eruption does happen, eventually leading to the case of expansion of the seafloor. Observe, this is the coastline of North America. And here you observe the region of the continental shelf across the Grand Banks, that is the region of Canada. And here you have the entirety of the hill like feature, that is your mid Atlantic ridge. Okay. Why they are in the minor category? Because, as if you compare the larger size of the ocean, they will not dominate the ocean. They are present only in smaller quantity. However, their extent is overall a continued ridge feature spanning for more than 70,000 kilometers. But still, they are present across this line. Rest of the ocean is either the sea floor or the case of certain deposits. Then you have another minor oceanic feature that is known as a submarine canyon. Just like a canyon on the land surface, this is a canyon which is created underwater. Narrow, deep, starting from the continental shelf, extending into the case of your area of continental slope and even extending on up till the region of the continental rise. Okay. Why which are in light green? This one. All of this, the color is dependent upon the depth. Okay. This is the least depth. This is the least depth. This is more deep. Okay. Again, the depth is decreasing here. So this color of green to blue, etc., is basically associated with the case of depth. Okay. Nothing supernatural is going on in these areas. Okay. Now, these submarine canyons puzzled geographers for a very long period of time, that how did these canyons get created? Initially, the idea was that look, wherever you have the rivers draining into the sea, it is in those rivers and riverine regions that submarine canyons will be created. But later on, it was understood that submarine canyons can be found in areas where the rivers move, in other regions also. Okay, let me show you the submarine canyon with the help of the map. So, for example, understand this, that the river is moving. It will bring certain amount of deposit, certain amount of materials. Those materials will then roll down, rub against the sea floor, and they will create a canyon like structure. If I show it to you in the case of the map, observe the region here and observe the white region here. I hope you are able to see a kind of a, basically, I hope you are able to see a kind of a black line in both these areas. Are we able to see this? This is where in the shelf region, River Indus, River Ganga, Brahmaputra, they have basically managed to create a canyon like structure. So that is where it was understood that wherever you have the rivers moving, there the erosion will happen, and there these canyons can always get created. Okay. But later on, it was realized that even where the rivers are not there, there also canyons can be present. Okay. So that is basically where you have submarine landslides, etc., which were deemed to be responsible. But there is another factor, what is known as turbidity current. This is responsible for creation of these submarine canyons. How? Creation of submarine canyons. And what is this turbidity current? Turbidity is derived from the term turbulence. Turbulence means what? Not a very streamlined flow. right? Turbid water is a general term used in English vocabulary. So that basically means water which is having lot of sediment, lot of sand movement, lot of violent movement, etc. Now, you will observe that whenever you have the sea waves which come in and then they go back, oftentimes they will erode something. They will carry some sand particles, rock boulders, gravel, pebbles, etc. All of that will be dragged across the sea floor and they will keep on rubbing against the sea floor. Okay. Oftentimes, these sediments, etc., when they drag against the sea floor, they gain a speed of almost 45 to 50 kilometer per hour as they are dragging against the sea floor. This movement of sediment, mud, ooze, pebbles, rocks, boulders scraping the seafloor continuously is known as a turbidity current. And that turbidity current, repeated action of that in a region will create a kind of a narrow canyon like structure that is known as your submarine canyon. Okay, I hope this is understood in detail. Now, then you have another underwater feature, what is known as a seamount and a guyot. Seamount is what? Underwater mountains. The moment that mountain is emerging above the water body, it becomes a volcanic island. But underwater volcanoes oftentimes create structures of small mountains which are not able to emerge out of water body. That is a sea mount, sea mountain. Now, let's suppose you observe this. This is a case of a sea mount, right? Volcanism continued, created a kind of a volcanic island. Okay. But here, this seamount will experience wave action continuously, right? This wave will erode it. So, this wave, what was the case of the water body? This was your sea flow. Initially, you had the seamount. Wave action from both the sides continuously will tend to erode this. Eventually, it will have a flat top. Okay. This flat top was for the first time discovered by whom? By none other than Harry Hess. Harry Hess observed this kind of a structure which is elevated and has got a flat top. Now, he basically was associated with the university that was Princeton. And in Princeton, they had a hall like this, a lecture hall like this, which was named after one of the great geographical minds of this century, of the previous century, that was Guyot. Goyat actually was a German geographer who fled to US and Princeton took him over and he was very instrumental in many of the geographical researches. He was made the chair of the geography department in Princeton. He was the head of department. Based upon Goyat's name, you had the hall in Princeton, lecture hall, which was named as Goyat. Harry has observed that lecture hall. He observed the same structure in the case of the underwater feature. He named this as Goyat. Okay. I hope this story helps you retain what is a Goyat and what is the name of a Goyat. So, a seamount, if it is eroded, a seamount which is eroded, it forms a kind of a Goyat. Okay. Marine erosion. This is volcanic in nature. Seamount is volcanic in nature. Okay. Now, then we come across to the physical feature, and that is the ocean temperature. Ocean temperature is not consistent everywhere across the planet. Obviously, even a general individual, if I ask them whether would you prefer Bay of Bengal or whether you would prefer the region of the Arctic Ocean, everybody would prefer Bay of Bengal, right? It is warmer. Arctic, much colder. So oceanic temperature does vary. This thermal image that you see on your screen is an evidence of the fact that oceanic temperature, when you talk about the southern hemisphere and compare it to the northern hemisphere, in the southern hemisphere, you will still find that the temperature variation is almost parallel to the latitudes. As you move into the higher latitudes, it keeps on becoming colder and colder. But look at the northern hemisphere. It is not uniform distribution. It varies. In certain areas, it will get very hot. In certain areas, it will get very cold. Now, when you study ocean temperature, you have to study it in two different ways. One is the case of horizontal distribution. What does that mean? Or horizontal variation. That means, let's suppose from 0 degree to 50 degree or 90 degree, north or south, how does the temperature vary across the oceanic surface? And then you also have the vertical variation, that as you move into the ocean depth, how does the temperature vary? So this is how you classify the case of ocean temperature. First, we will take a look into horizontal variation and the factors influencing the horizontal variation of temperature. There are a few factors. For example, latitude is a major factor. Just like temperature on the land, we studied that temperature varies from one region to another. What were the factors? Latitude was a major factor. Here also, latitude is a major factor. Lower latitude, greater amount of heat, greater amount of solar insolation. That is why temperature will be high. Average temperature in the lower latitude is roughly 26 degrees to 27 or 28 degrees Celsius. Extreme cases, 30 degrees, right? 32 degrees, 33 degrees. This has to deal with the solar insolation. Right now, we are dealing with what is referred to as the Godzilla El Nino. That is the case of the warming of the Pacific Ocean. You observe the temperature in the Pacific in certain areas, it has crossed the 30-degree mark as well, right? Now, as you move into the higher latitude, observe it gets colder, cooler, and then colder because of reduction of solar insolation. Okay. Now, then you have unequal distribution of land and water. Observe this map on the background. But before that, we had discussed something earlier in climatology. We had discussed that land heats up very fast, heats up very quickly, isn't it? Cools down very quickly as well, isn't it? Right? So basically, land heats up very quickly, cools down very quickly as well. Now, if you observe, let's suppose a region like the southern Indian Ocean. And if you observe this region, Bay of Bengal, Bay of Bengal is closely surrounded by land. As the land gets very, very hot, Bay of Bengal will also get very, very hot. Temperature will increase. Okay. So that is where Bay of Bengal temperature will depend upon heating of the land. Right. If you consider this region, let's suppose around the area of the Hudson Bay in this area. Now, in the region of the Hudson Bay, if you observe here, it is surrounded by very cold land areas. So this will also be very cold. So unequal distribution of land and water will mean wherever you have very colder land, water body will also become very cold. Wherever you have very hot land, water body also gets hotter. So that is the role of the land and water. That is why oceans will be warmer in which hemisphere? Northern hemisphere or southern hemisphere? Where will you have the ocean temperature to be very, very high. Always, oceans will be warmer in northern hemisphere. Always. Why? Because northern hemisphere is dominated by land. Southern hemisphere is an ocean hemisphere, whereby you have dominance of the water body. That is why in southern hemisphere you will observe that the temperature change is almost parallel to the latitude. Right? Northern hemisphere, hotter portions are more. Okay? That's why fisheries in the northern side, absolutely not. That has got nothing to do with more fisheries in the northern side. Fisheries and the existence is based upon multiple other factors, ocean currents, that upwelling, etc. There are multiple other factors which leads to the fisheries, not the warmer temperature. In fact, higher temperature is not good for the biodiversity. Whenever you have higher temperature, biodiversity generally is impacted. Then you have other factor. That is the case of the prevailing winds. Prevailing winds means the existent wind pattern or the permanent wind systems. Permanent wind systems. Okay. Now we had discussed that you have the trade winds, the westerlies, the easterlies, etc. Let's suppose we consider those winds. In this region, on the west coast of Africa, I will have the presence of trade winds, right? Here also I will have trade winds. But what will these trade winds do? On the west coast of Africa, can I say these winds are offshore? Can I say they are offshore, moving from land to water? And in these areas, can I say they are onshore, moving from sea to the land? Can I say so? Right? Now, what is the consequence of that? Consequences that here, imagine you have the offshore winds in this animation. Offshore winds mean what? When you consider the case of the offshore winds will basically drag the surface water along with them. The warm surface water is dragged away, which means what? The colder subsurface water will replace the vacancy, will rise up. So, what will happen to the sea surface temperature in this case? Because the cold water is coming up, this is known as upwelling. Upwelling is going to be associated with offshore winds. UPSC has asked a conceptual question associated with this. We will discuss that tomorrow. This upwelling, what will be the impact on the sea surface temperature in this case? Sea surface temperature reduces. Why? Because the colder water has replaced this. Okay. Now, if let's suppose the wind is onshore, meaning what? It is dragging more warm water along with it. Now, all that warm water is accumulating in the coastline. So, what will happen to the case of the onshore winds? Here, the water is forced and pushed downwards. That is what is referred to as downwelling. And what will downwelling lead to? Rise in temperature. Isn't it? Apply that logic and now tell me something. If I give you the cases, okay, now here When you observe the different regions, you have the westerlies, the trade winds, etc. You have all these. This is your South China Sea. What will happen to the sea surface temperature in South China Sea? Will it be high? Will it be low? The temperature will be high. You have onshore winds. What will happen to the sea surface temperature in Bay of Bengal? Will it be high? Will it be low? It will be high. Onshore winds, downwelling. What will happen to the sea surface temperature on the western coast of Africa? It will be low because you have offshore winds, isn't it? That means upwelling. What will happen to the sea surface temperature in the region of Gulf of Mexico? It will be high. Onshore winds. What will be the sea surface temperature in the coastline of Canada? It will be low. Offshore winds. Coastline of Britain and Europe, high. Onshore winds, isn't it? This is the reason that certain areas of the planet, they are very prone to tropical cyclones because the sea surface temperature naturally goes very, very high. That is why South China Sea, Bay of Bengal, the region of Gulf of Mexico will always experience a lot of these tropical cyclones. Okay. Now, then another factor which will influence the ocean temperature in various different areas is the movement of the ocean current. Just like warm winds will increase the temperature, cold winds will lower the temperature. Similarly, when you talk about the warm ocean currents will always increase the temperature. Cold ocean currents will always tend to lower the temperature. Okay, so that is basically why you will observe, particularly in the region like the northern Atlantic. Okay, northern Atlantic, you will observe there is so much amount of warm water. It tends to remain ice free for most of the year. This warm water is brought by the North Atlantic current, the Norwegian current, and so on. And that is why it is much more warmer, right? Whereas you will observe that water in certain areas like Southern Ocean, etc., or even, for example, the western coast of South America, right? The region of west coast of Africa, you have cold current, colder oceanic temperature. Okay. Why do you have cold current in the west coast of Africa? Offshore winds. Now you know the reason as well. Then we come to the vertical variation in temperature. How does temperature vary as you move across the depth of the ocean? So, oceanic water can broadly be divided into two categories. Overall, there are multiple categories. You have the photic, aphotic, transition, etc. But broadly, your NCRT gives me, NCRT doesn't give me that liberty, but broadly, you have the classification as photic and aphotic. Photic, sunlight is available. Aphotic, sunlight is not available. This is the region of permanent darkness. Now, in region of permanent darkness, temperature will be high or will it be low? That region will be very cold. Whereas in this area, photic zone, still you will have the case of higher temperature. You will have a higher temperature. Here you will have the case of very cold conditions. Now, all the factors that we have talked about till now, that is the factor of latitude, the factor of upwelling, downwelling, the factor associated with these ocean currents, prevailing winds, unequal distribution of land and water. They will primarily impact the surface one or they will impact the depth of it too. What will they impact? All of them will impact the surface. Those are surface phenomena. That is why from one region to another, you will observe there is a variation in the oceanic temperature on the surface. Whereas at the bottom, the oceanic temperature is consistent. That is roughly around 3 to 4 degrees Celsius. Here you will have consistent temperature. Temperature. Here you will come across variations. But there will be a zone of transition. That zone of transition will come here. As you move from in the depth from the photic to aphotic, suddenly there will be a drop in temperature. That is what is referred to as the transition zone. Transition zone is also known as thermocline. So if you observe this phenomena, you will observe that at the surface, basically, there is a temperature of 24, 25 degrees Celsius at the surface. At the bottom, it is constant around 4 degrees Celsius. But there is a zone of transition. This zone of transition is representative of zone of transition. This indicates the movement from photic to aphotic zone. Okay, so that is your thermocline. Thermocline is nothing but zone of transition. Okay, at the bottom, because the surface phenomena won't have much of an impact at the bottom, that is why at the bottom it is almost consistent. Okay, then we come across the next part, the last part, that is the salinity of oceans. Ocean water is salty. It has got the presence of salt, different types of salt: calcium sulfate, sodium chloride, potassium sulfate, magnesium sulfate, etc. Now, how much of salt is present per kg of ocean water? That is the measure of oceanic salinity. Okay. So, for example, if you consider 1 kg of ocean water, let's assume 1 kg of ocean water. In that 1 kg of ocean water, let's assume that you have 36 or 35 grams of salt, right? That basically indicates your salinity. So, salinity will be 35 gram per kg. That will be represented how? 1 gram, 1 kg is equal to 1000 grams. So it will be represented as parts per thousand. This will be represented as 35 parts per thousand. We had the similar expression when we were discussing specific humidity, if you retain, right? This is also represented by the symbol parts per thousand. Okay, that is your oceanic salinity. Now, where does the ocean get its salt from? When we talk about calcium sulfate, magnesium sulfate, potassium sulfate, chloride, all of them, where do the oceans get that from? So basically, there are multiple different sources of salt addition and also multiple different sources which remove the salt. For example, when we talk about, let's suppose, volcanic eruption, underwater volcanic eruption, or above ground volcanic eruption, the ash, the materials that get dissipated in water, that will add some amount of chloride, sulfate, carbonates, etc. So that is one of the primary additions of the salt, right? Then, other than that, let's suppose a river is moving. River will erode certain materials and will deposit them into the ocean. That will also add some amount of salt. On top of that, let's suppose you have the ocean next to a larger rock or a mountain. Slowly and steadily, it will dissolve some minerals out of the rock or the mountain. that also will add salt. So, like that, you have multiple such additions which keep on adding salt in the ocean. But then, a pertinent question, think about it. When we talk about the oceans, oceans were created 3.5 billion years ago, almost, right? 3 to 3.5 billion years ago. Since that point of time, all these factors have continued to add salt into the ocean. But still, the average salinity of the oceanic water is fixed at 35 parts per thousand. Ideally, if salt is being added for billions of years, overall quantity of salt would have been very, very high. Why is it restricted to 35 parts per thousand? The reason is that the salt gets dissipated as well. Over a period of time, that salt gets dissipated. How? Let's suppose in the oceanic water, you have multiple dissolved salts of certain compounds. There can be a possibility that few of them can combine together, form a larger chunk, and then they will get deposited. So it is no longer dissolved in water, no longer counted as salinity. On top of that, let's suppose across the coastal area, there is very violent sea wave which is generated. Now, if you go to the coastal area, you will observe a huge amount of spray generated by the sea. Those particles also carry some amount of salt. And you know what? That sea spray generated from the oceans sometimes can be carried by the wind. As it is carried by the wind, those particles oftentimes are carried into the upper troposphere. The salt remains, water is evaporated, and those particles help in buildup of clouds. Okay? Are primitive oceans not saline? They were also saline. In fact, they had huge amount of sodium, huge amount of various different type of uh, the carbonates, etc. That was present in abundance amount. That is why the first life actually germinated from the region of the oceans. Okay. Now, these are the type of salts which are present. The most dominant salt in the ocean is your sodium chloride. Most dominant, which is almost 27% of the overall salt content is your, or rather 77.8% is the overall percentage of sodium chloride. Then you have magnesium chloride, magnesium sulfate, calcium sulfate. Rivers majorly bring calcium sulfate. The rivers, when they bring this various different amount of salt, they carry huge amount of magnesium sulfate. Okay. So for your prelims, I would advise the first three you should retain, which is the most dominant, sodium chloride, right? Then magnesium chloride, then magnesium sulfate. Okay. Oh, my bad. Rivers bring calcium sulfate, not magnesium sulfate in majority. Okay. Then here also you have the horizontal and the vertical distribution of salinity, just like temperature. How does salinity vary? And why does salinity vary? Now, it is very simple to understand. If you apply the basic logic of addition and removal of water, let's suppose you consider the case of a water parcel. It will have water droplets, isn't it? In between these water droplets, let's suppose you have the presence of salt. Okay. Now, let's suppose there is evaporation. Evaporation means what? Evaporation basically, will the salts also get evaporated, or will you have only the case of water getting evaporated? You will come across the case where only water droplets get evaporated, salt gets left behind. So, in this water section, after evaporation, water droplets will be comparatively lesser, salt will be left behind, isn't it? So, what has happened to the case of your overall salinity or salt presence? Let me represent it by the same color. I will represent the salt by this dashed line. As compared to earlier, the proportion of salt per molecule of water is higher. So, whenever you will have the case of evaporation, salt concentration increases. On the other hand, in this situation, let's suppose I have rainfall, precipitation. Rainfall will bring fresh water, it will not bring salt along with that. That means the water concentration will be higher per molecule. Salt concentration will be comparatively less. So that means salt concentration has decreased. What do we gain from this? Why have I told you this? To give you a basic understanding, a basic general principle. What is the principle? Any principle or any process under which you observe addition of water, net addition of water, okay? Wherever you observe a net addition of water, that means salt concentration has reduced in comparison. So salinity reduces. Anywhere where you observe net removal of water, like evaporation, net removal of water, in that case, what happens to salinity? Salinity increases. Maintain this basic concept. Horizontal variation or regional variation of salinity is solved just by this basic concept. How? Let me show it to you. When does salinity increase? Evaporation means removal of water. Salt is left behind. Salinity is increasing. Freezing. When seawater freezes, whenever you have freezing of seawater, majorly water will freeze or only the salt will freeze. Majorly the water will freeze. Again, removal of water from the region. Salt is left behind. Net removal of water. Again, increase in salinity. Salt concentration in the water is more. Now, let's suppose there is precipitation, rainfall, net addition of water, river runoff, net addition of water, groundwater discharge, net addition of water, melting of ice, net addition of water. Means concentration of salt is decreasing. Whenever you have net addition of water, concentration of salt is decreasing, means salinity is decreasing. Okay. So freezing, evaporation will lead to increase in salinity, uh, rainfall. Then the case of river runoff, the case of precipitation, all of them will lead to a decrease in salinity. Concept is understood, right? Observe this. If you observe this mapping, this is the case or this is the graph which indicates the rainfall and evaporation distribution from the equator to the polar region. If you observe the region of equator, red line indicates rainfall, blue line indicates evaporation. If you observe the region of equator, rainfall is high, rainfall is high, Evaporation is also there, but evaporation is comparatively less. Will evaporation also remove little amount of salt? Think about it. Do it at your home itself. Take a glass of water, mix some amount of salt in it, keep it on your balcony, and then observe that after evaporation, is the salt left behind or not? Evaporation will never carry the salt along with that. Because please understand what is evaporation. Understand that basic concept. What is evaporation? Liquid water droplet when it is converted to water vapor. That is evaporation. Now, when it was liquid, it had managed to dissolve solid salt compound. Can that solid salt, NaCl, can you convert it into gas? Can that be converted into gas in the case of your normal conditions? Absolutely not. Right? When we say that the sea salt can form the nuclei in the air for clouds, it is generated from your sea spray. Sea spray is when you have large sea waves hitting the rocks and then generating a kind of a spray. These microparticles of water will have embedded salt in them. That microparticle of water with the salt is carried to the upper atmosphere. That is what will become the hygroscopic nuclei. It will never be the case of evaporation. It can never happen that NaCl or magnesium chloride or magnesium sulfate at normal temperature can get converted into gaseous state. That is where science oftentimes comes to your rescue. Now, at equator, rainfall is high, right? Comparatively, the amount of evaporation is less. Evaporation, even though, is very high at equator, but still, comparatively, it is low. Then you come to the subtropic. Subtropic is where you have sinking air. In the region of sinking air, you observe what? Evaporation is very high. Rainfall is comparatively low because this is a region of high pressure. Sinking air, no rainfall. Salinity is, that is why, very high because evaporation is high. So salinity is highest. Where? In the tropics. Always. That is why the most saline water bodies, be it Dead Sea, Lake Van, right? All of them will be found in the region of the tropics. And that too, northern tropics, not even in the southern tropics. Why? Because comparatively, temperature in the northern tropics is going to be much higher. So that means more evaporation will happen. Okay? The general trend, however, will be that salinity will reduce. General trend is salinity reduces from equator to poles. This is your generic trend. I want you to learn from this map. Observe this map. Observe blue color represents low salinity, red color represents very high salinity. Observe the blue color, Bay of Bengal, very low salinity. Why? Large number of rivers, Iravadi, Barak, Brahmaputra, Ganga, Mahanadi, Krishna, Godavari, Kaveri, all of them drain into the region of Bay of Bengal. So, addition of river water, lower salinity. Observe this region. Mekong, larger rivers drain here. Wango drains here. Right? This region, Congo drains here. Low salinity. Observe the region of Mediterranean. Very high salinity. Why? Not much of a river drains into Mediterranean. Surrounded by land areas, so temperature will be very high. In the tropics, so rainfall will be very less. Evaporation is also high. Hence, Salinity is very high. Then observe the region of Red Sea, closely surrounded by land. And this land doesn't receive lot of rainfall. So that is where you will find that basically temperature is very high. Not no river drains here. Temperature is very high. Evaporation is very high. Salinity is very high. Observe the region of Black Sea here. Salinity is comparatively lower. Why? Basically, because there you have Danube, Don, all these larger rivers drain into Black Sea. Influx of river water reduce salinity. Observe the salinity is high in the region of northern Atlantic. Why? Warm ocean currents mean even at higher latitudes there is evaporation, which means you have the case of higher salinity. So it is basically governed by the simple principle of addition and removal of water. You follow that logic, you will never need to learn anything out there. Okay. Then you have the case of the variation of salinity with depth. So all these factors that we have talked about, addition of water, removal of water, if you consider the depth of the ocean, let's suppose this is your surface, this is the depth of 5 kilometers. Rainfall. Will the rainfall impact the surface or the depth? Always the surface. Evaporation, when it happens, will it impact the surface or the depth? Always the surface. So all these are surface phenomena. So salinity at the bottom is consistent, just like temperature at the bottom is consistent. And how much is that? Around 35 parts per thousand. But salinity on the surface is different. Salinity at the tropics is the highest, right? It can go up to, for example, Red Sea can be 41 parts per thousand. Lake Van in Turkey can be having a salinity of 330 parts per thousand. That means in 1 kg of water, you will have 330 grams of salt. Dead Sea can have a salinity again to the tune of more than 200 parts per thousand. So these are very saline water bodies, all in the region of the tropics, right? So that is where you will have a zone of transition from variation on the surface to consistency at the bottom. That zone of transition is what is known as halocline. Observe that basically at the tropics, salinity in general 35, 36, 37, even 41. At the higher latitude, salinity is much lower because evaporation is very low. At equator, roughly around 35. So this is a zone of transition. Zone of transition. And that zone of transition is what is known as halocline. So halocline, how big it is, how big of a variation it is, that will be dependent upon which latitude you are in. For example, at the region of equator, you will have the variation which is almost minimal, right? At the region of the tropics, variation is high because at the base you have 35 parts per thousand. Okay. Now, this is where we come to the end of the discussion. The doubt, please explain turbidity, current, and wave erosion once. I'm a bit confused because you said erosion of seamount leads to formation of goyads, and not all seamounts are seen at the top of ocean. Turbidity current is not going to cause your goyard formation. Do we have fresh water reserve as we go deep? No. Ocean water is saline. At the depth underground, you have certain aquifers of rocks which have permeable water that is fresh, but it is not within the depth of the ocean. Okay. Now, please understand, Tarak, that when we talk about the case of turbidity current, it is not going to create the case of what is turbidity current. Understand, everyone, this is the last topic. Please listen to this carefully. What is turbidity current? Turbidity current is where you have, let's suppose, the wave which is coming in, it is carrying some amount of sediments along with that. Those sediments are going to roll down with an increased speed. This motion is known as turbidity current. Turbidity current. Okay. When we talk about, let's suppose, the case of a seamount, underwater volcanic eruption has led to the formation of seamount. This seamount will be basically eroded by the water itself. Water movement continuously will lead to the formation of a flat top like structure that will be referred to as a guyat. Okay, this is what is referred to as a guyat. So it is basically very, very different. Okay, because Deepika, the evaporation is zero in the region of the poles. Now, that brings us to the end of the discussion for the day. Tomorrow is going to be the last session in our entire journey for NCRT. We will be discussing ocean currents, waves, and tides. Join us tomorrow and finish the entirety of the NCRT. And tomorrow you can say that your fundamentals of physical geography, the conceptual portion of physical geography, is absolutely clear. So we'll meet again tomorrow. Till then, take care. Now, I will ask you a question. Let me know the answer to that in the option or in the comment section. The question is that out of the two water bodies, that is, the water body of Arabian Sea and Bay of Bengal, which one has got a higher salinity and why? Let me know in the comment section. Take care of yourself. Goodbye. Thank you.